Okay, we can make a start. We got a bit of a grab bag of things in the lecture today. We've got one last topic on the wave equation. Um, Remember last time we had a sort of a semi-infinite um, a spatial domain and saw that we could describe what was going on with the tool that we developed. D'Alembert's principle, which really comes from these kind of characteristics in the vector problem. And we could describe what was going on with the idea of some reflection happening off that boundary condition. On the next assignment, you'll see there's a different boundary condition and you get different behavior. Now we're going to look at the wave equation in a finite domain with boundary conditions on both sides. It's more appropriate there to go back to our series solution ideas of things. So we'll do that. And then that ends our wave equation discussion for a little while. We're then going to derive Poisson's formula for the disk, which is the solution to the Laplace problem in the disk, funnily enough. So that's a circle. You've got the Laplace problem inside, so Laplacian of u is equal to 0, and you're given data on the boundary of the circle. There's a formula for that. You might have seen that already in a complex variables course, but I wanted to at least have one more thing reminding you of elliptic problems, so you have in your head the sort of big three problems we have in second order partial differential equations in two-dimensional space. They are the heat equation, the wave equation, and the Laplace equation. Because then we go to a really standard topic in a class like this, which is we showed that there's a whole class of problems that really, once you transform coordinates, you can show fit into one of those three problems. So they're really kind of generic problems, and that's why we studied them, because even things that might look more complex really fall into one of those three bins, and then your experience with those that you've built up in Math 400 will tell you how they're going to behave. So if it's a model of something that comes to you of some physical phenomenon, you'll have some insight into it. And if it's going the other way, where you have some insight into a physical phenomenon that you want to write mathematical equations for, so you can, do some computational work maybe later on, you have an idea of what type of equation you should end up with that makes sense. Okay, so we'll start with the wave equation stuff. We have the wave equation in here. We're going to have initial conditions. This is the values of u. And we also have started calling the other initial conditions that we could give, which are the time derivatives. Let's give those to be 0. This is something where we can figure out either with the last trick I showed you last lecture, or just by straightforward similar computations to what we're doing, how that goes. So this is x and t. And so last time, there's a quick question coming up. Good to ask questions at the beginning before we get into the gritty details. I was wondering if you would consider changing the due date for next week's homework. So that's the one that's already posted, from Tuesday to Thursday night. A bunch of people have 3 midterms next Wednesday. Ow. Okay, let me just see. We're planning, I have a midterm for you guys planned, midterm number 2 on March 16th. And that's next week. Okay, so I guess I could do that. But then you won't have solutions to that assignment due before the midterm. So there's a question for you guys. Should I make a poll asking what you want?
Yes, make a poll.
Yes, make a poll. Okay. Okay, so now I have to edit. Okay, give me a second. I don't have this poll ready. I'll make it anonymous. I'll say postpone assignment number 6, due date to Thursday. And now you know the consequences, right? There'll be some solutions that you don't have. And we've got yes and no. Save. Okay, so launch the poll. You 19 few people who are here have more power because, okay, you're here. I can actually ask you. Okay, there's one more person.
Someone says they can't seem to vote.
Nirab, are you willing to put in chat what your vote would be? It's
You
not.
can also, you could put it to just me or Brian as well if you want to be anonymous.
Yeah, except there's only one person, and we say the vote has changed from one to something else. I'll say, Nirab, even if you voted, we have a winner. So your anonymity can be preserved. So a narrow margin, but we'll keep the due date for Tuesday. So I would say, oh, sorry, I should share the results. So I'll say we'll keep the due date at work beforehand as much as you can and hand it in early. I'll make sure to have solutions posted timely, so you'll have them available for the midterm. Okay, reasonable thing to ask, but we have not a particularly clear answer, but an answer from the poll. Anything else you guys want to bring up before we get into the material proper? Oh, on the 16th, you're right. It's on the 17th. It comes out midnight of the 16th, and then you'll have it all day. Now, I can. There was a request last time that the midterm. Oh wow, we can do another poll. That the midterm be released at 9 in the morning on the 17th to 9 the next morning. Do people want that? There was a concern, I remember last time, that if it was released at midnight, people would, you know, stay up so that they could, I don't know, like they wanted to see it.
Last time you released it at 9 p.m., didn't you? And then it was due like at about midnight.
Yeah, yeah. I could do that again. Okay, but why don't we waste another 2 minutes? I'll make another poll. Okay, and then you guys can tell me what you want. I don't really have a fight in this. Okay, so midterm start times. Okay. Again, you intrepid real time lecture participants can, oh, okay, it looks like there's a clear winner. Okay, one more person to come in, but there's a clear thing. I'm happy to do that. And for those of you that are in cohort, you can let your colleagues know that this will happen, and I'll make an announcement at the end of the lecture on the Canvas page that this will be the time. Okay, anything else to bring up before we start talking about series solutions of the wave equation? Okay, so we were looking at this problem last time where we had a hard boundary on this side, and we saw we got an inverted reflected wave from that boundary. And so you know in your heart of hearts that if I do this problem, right, I could describe this solution as a sequence of waves reflecting back and forth from those boundaries. And that's a useful physical way to understand the phenomenon that's going on here. It's not a particularly useful way to describe the solution. And so what we're going to do is we're going to go back to series solutions. So we're going to consider the PDE in the form UTT is this boundary value operator, where this is the second derivative and boundary conditions with the two Dirichlet homogeneous Dirichlet conditions that we've had before. Okay, and then we would naturally look for solutions. In terms of the eigenfunctions of that boundary value operator. Is there an analog of D'Alembert's formula for higher space dimensional wave equations? No, there isn't. That's another interesting thing. The wave equation in higher dimensions, well, has interesting distinct behavior from the behavior in 1D. That's a past Math 400 topic. You may touch upon it in some physics courses that involve waves. But yeah, good question. Unfortunately, the answer is no, right? This 1D behavior is really, really special. Okay, so this boundary value problem, like you've seen it 3 times already in this course, and you saw it in your first foray into PDEs, which might have been Math 257 or something. It's the sine series, right? So we already know it's the sine series. We could have done separation of variables, except I'm hoping, we're a little bit more sophisticated in this at this point, and we can just go, it's going to be the sine series from this argument. So I'm going to look for solutions that are in the sine series. A spatial sine series. Okay, so I know that this is going to come out. I can see it from the structure of the problem. And so now we're not talking about waves reflecting back and forth. We have a fixed spatial envelope with a time varying amplitude to that envelope. And these things are going to be called standing waves. So this is a standing wave series. And there's no damping in the wave equation that we have now. There's a question, I think, on the next assignment where there's some decay. But if you look at the standing waves, you can also talk about them in the wave equation with damping. And the damping rate increases with n. So it's not something you can see from this equation, right? We're going to see that these things, whatever they start at, they just keep going, just like there's no damping we've seen in the waves that we've had from D'Alembert's formula. But if you put damping in, then this series starts to become significant because just like the heat equation, it's the first few that really tell you what's going on, right? And if this was some sort of music instrument, right, then these would be the n equals 1 mode would be the dominant note of the instrument, and the other ends would be the harmonics. Okay, so I'm going to put this into the wave, wave equation. When I take the 2 spatial derivatives on the right-hand side, right, I just get a multiple of minus n squared pi squared, just like we've seen before. And then we separate out the coefficients. And I'll get the second time derivative of these coefficients is minus n squared pi squared times Cn. Now, when this was the heat equation, we just got Cn dot, and then we got exponential decay. But now with the second derivative, this gives us oscillatory behavior. An sine n pi t plus bn cosine n pi t. And now I'm going to match the initial conditions. the time derivative initially is 0, right? And this thing corresponds to the time derivative at time 0, right? When you look at the time derivative, you get a sine term over here, which doesn't appear. So I get an equals 0. This is from u1 of x is 0. And I get bn then is pretty clearly the sine series coefficient of the initial data. Okay, so that means I'm going to put this together. I'm going to get my u of x and t. It's going to be a sum of these standing waves. And now I see how they behave in time. And I know what the coefficients are going to be in terms of the initial data. Scroll up. Scroll up. How far do you want me to go? That good? Okay. I'll let you look at this and then I'll scroll back down. Okay, another question coming up. Are there cases where you are unable to differentiate Cn? So what's interesting is you could imagine that you gave discontinuous initial data, right? Right, which is fine for the wave equation, right? It's just the discontinuity, moves with speed 1, goes back and forth. In which case, this derivation doesn't work, right? Because you're going to have discontinuities in time, right? Which don't match up here. But funnily enough, the formula that we end up with still works. Okay, so this series will converge to the discontinuous solution. So yes, there are cases you have to be careful, but not in this particular case. This I'll put a note here, right? This will define a weak solution if u0 of x, well, for this to make sense, right, u0 of x would actually have to have 2 continuous derivatives, right? So we can say it doesn't have to have 2 continuous derivatives, doesn't even have to be continuous, right? Is discontinuous. So good question, but in this case, the gods smile upon us. The gods of convergence smile upon us. Okay, so one thing I should have done is to have prepared, because you should be asking. Well, I don't know if you should be asking. One of the questions you could ask is, what about D'Alembert's formula, right? This doesn't look like D'Alembert's formula with the wave going to the right and a wave going to the left. So there's a trig identity where you can write this as a combination of a right-going wave and a left-going wave. It's a trig identity. It will be cos of n pi x plus t, and then there'll be some trig function of x minus t, n times pi times x minus t. So trig identity. I don't have it prepared, and I don't have trig identities in my head, except the really trivial ones. Trig identity goes to D'Alembert's formula. So this is completely consistent with that. It's just a different way of writing the solution. So let me put in the u0. Oh, no, sorry. That's not where I want to put the u0. I'm going to put in the u0 into the Bn, and I'm going to say I can write u as the sum cosine n pi t sine n pi x times the integral of 0 to 1 at u0 of x. Oh, why don't I use a dummy variable? That would make this formula a bit better than what's in the notes. Sine n pi s ds. Okay, so this is not how you typically write things, but let me just say, if I took the integral out, right, I could recognize this as a Green's function for the problem. Now, it's a Green's function that involves an infinite sum, so it's not particularly useful, okay? But nonetheless, for some theoretical purposes, it could help you. And just to remind you of the kind of theoretical stuff we were doing before, this formula here is a form for that map, which is you get the solution from the initial data with 0 initial time derivative as a map from the initial data to the solution at time t, okay? Where we were thinking of this as the whole function of x, this is the whole function of x, and so this is a formula for that in this case with boundaries. Okay, and again, this is something where you see on the next assignment a mechanism where damping can come into the solution. And in that case, on the next assignment, you'll see why the series solution actually gives you more information than you kind of think. Doesn't look particularly useful here, but when you have a problem with damping, it's the lower order n modes that last the longest. And so it's interesting again then to look at the first few terms and see what they're doing. It gives you some insight into what's happening. Okay, now, once we've written this thing into the form, UTT is L times U with boundary conditions for L, then, we can apply our Sturm-Liouville work. So we don't have to have just a simple string stretched between 2 points. We could, have all kinds of fun things happening. So we could look at a variable mass per unit length on the stretched spring that is the vertical displacements described by this wave equation, the linearized displacements. So I can have a variable mass per unit length. I'll call that mu of x. I think that's what was in the notes from lecture number 3. And then we would get a wave equation that looks like this. Right, this is for this particular application. If you thought of u as being the vertical displacement of that stretched spring, then that's the acceleration. So this is like a mass times acceleration is force kind of relationship, which you could go back to the notes and see. Right, I'm going to say that it's scaled in space and time. So I've got my homogeneous Dirichlet boundary conditions. I haven't made the boundary conditions more complicated in this problem, but you could. Right, and so the Sturm-Liouville problem that we would want to consider then, right, is phi double prime is lambda mu of x times phi. This is what you would get if you did separation of variables also, right? Okay, and so we know with the mu of x positive that all the lambdas are negative. That was an argument that we had on an assignment. And then these eigen functions are the shapes of the standing waves. And remember, we had eigenvalues of minus n squared pi squared, and we got angular frequencies of n times pi. Right, and so in this case, we'll have these waves will have angular frequency, which if this was a musical instrument, this is what you would be hearing, the square root of minus lambda. Okay, so we can do all of those things. Now, here is where you would actually have to go back to the derivation to work out what happens when you have mu discontinuous. So you have two different types of string, tied together in a knot, right? This is you're looking at the infinite, the Cauchy problem for that kind of situation in the in one of the assignment questions. I can't remember if it's the assignment coming up or the one after that. So this is a little bit tricky. This is, in fact, why I did the modeling work rather than just like say, here's the wave equation. So if you've got a case where mu is discontinuous, remember for the heat equation, some of the coefficients when they were discontinuous, there's different things that can come out with the junction conditions that happen there. So you have to go back to the derivation of the equation to work out what happens here. Then phi and phi prime are continuous at the discontinuity. So you notice on the assignment question with the two wave speeds, with the two different wave speeds, right? Because that's what this is going to do, is going to give you different wave speeds. That when you have two different wave speeds, you notice that the conditions there were that the solution and its x derivative were continuous. So that's a physical argument you have to make to figure out what are the right conditions to use at discontinuities. There's different ways to do that. Okay, if you go back and look at the argument, if phi prime is discontinuous in the string which has, at leading order uniform tension, then you have a force on no mass. Basically, and so that has to be continuous. Okay, so now there's a whole new slew of Sturm-Liouville problems that we could look at, which had relationships to wave equation problems, right? But that's sort of old news. So I just wanted to point out that all of that knowledge also applies to these wave equation, standing wave kind of representations. That ends our wave equation type work. Is UTT equals UX an interesting problem? Okay, so this came up in the chat. What about UTT is UX? Okay, well, I guess I got a couple of answers, right? If you've just labeled things wrong, right? And it's actually UT is UXX, then it's the heat equation. So then it depends on what kinds of initial conditions you give, right? So if this is a Cauchy problem with t, like really time, and you've given on t equals 0 values of ut and u, is this a well-posed problem? Okay, is it interesting? Okay, that I don't know. Like, is there some physical, thing? I can talk about what its behavior is and whether it's well-posed or ill-posed. And coming up in a few lectures, I will show you a technique where we could answer that question easily with just a little bit of algebra. So I'll postpone it till then. I'll use this as an example then, if you're okay with that. Okay, I see sure in the chat. Okay, good. Okay, so we will have a magic recipe to figure out whether problems are Cauchy problems are well posed or ill posed, and a little bit of what their behavior might be like. So, like I said at the beginning, at the end of this lecture, although we got distracted a little bit at the beginning with some sort of administrative things that were good to address. So this might be next lecture before we get to it. But we're coming up to the there's only three. It's not there can be only one. There can be three types of equations that come out of second order linear partial differential equations in the plane. And so I wanted to remind you of one of the other three that we haven't seen much of, and to come up with something which sort of fits in with what we're doing, because it's another series argument, and it'll also be useful later on in maximum principal argument for the Laplace problem. And so let's do it. This is Poisson's formula in the disk, right? And just to be confusing, Poisson's formula is formula for the Laplace problem. I guess, I don't know. Did Laplace and Poisson know each other? I don't even know if they were contemporaries. We haven't seen much of these elliptic equations. These are the really the extensions of our 1D boundary value problems, right? So I've got a disk. I'm going to have Laplacian u is equal to 0 in the disk. That makes it the Laplace problem. If Laplacian u is equal to f with 0 boundary conditions, that's the Poisson problem, funnily enough. And so I'm going to have Laplacian u, that's uxx plus uyy. But of course, it's in the disk. It's pretty, it's going to be the unit disk. It's pretty natural to write this in polar coordinates. That's 1 over r r plus 1 over r squared u theta theta. Okay, so pretty good. And this is characterizing these types of problems, elliptic problems, is that you need boundary conditions around. One boundary condition all the way around. Whereas for the second order heat equation, you needed 2 initial conditions on the same line. These are sort of the fundamental difference in character between those equations. And we'll see if you try and give the wrong kind of data for the wrong problem, you end up with an ill-posed problem. That's coming up in the same form where we can answer the question of what about that equation UTT is UX. Okay, so the Poisson formula, you have to give data on the boundary. Okay, so that's going to be, this is u, if I'm talking about u of r and theta, this thing here is u1 theta, because this is a unit disk. I'm going to give data all around, and I want to figure out a solution that satisfies uxx plus uyy is equal to 0, but has those data. So I'm going to do a series solution, right? And a good place to start is with the Fourier series in theta. So let's do that. So I'm going to look for a solution in the form which I know will work. I don't know if it's going to go in, well, okay, I do know it's going to go somewhere interesting, but you don't necessarily know beforehand. This would be something that someone would have tried. I'm not sure exactly how Poisson derived this formula first. Like I say, there's a complex variable argument you can use as well. I don't know which one was more sophisticated, this kind of thing that I'm doing now, or the complex variable argument. Okay, and then if you put that into here, we don't get Bessel functions, by the way. There's no, we're Bessel free today. I get 1 over r times r un prime. Un is only a function of r, so prime is the derivative with r prime. Minus n squared over r squared un is equal to 0. Okay, and I can multiply through by r. And I know that I've got to have un at 1 is equal to gn. That's the nth Fourier term of g of theta, right? That's the 1 over 2 pi, the integral from 0 to 2 pi. What sign did I use for the series? Okay, so this is g of theta e to the minus in theta d theta. So I'm just matching Fourier series terms. Okay, this is a second order problem. And this is a game that we're gonna, I think we've come up with already when we talked about Laplace problem in the sphere. It's a second order problem, right? You need to give 2 boundary conditions. And so there's a hidden one here, which is that un at 0, this has to be bounded. Okay, we're going to have solutions where there's going to be one kind of reasonable solution at 0 and one that has a singularity at 0. And that's where we're going to be able to say, oh, the coefficient of that one is 0. That's like having a boundary condition at 0. Okay, so like many of the times in the past, even earlier in this lecture, we've made progress on the analysis of a partial differential equation by reducing it to a infinite series of ODEs, right? So ODEs are something that's pretty concrete. We got an infinite sum of them, but at least we can make progress on these. Now, if you took an ODE course when I took an ODE course, my first ODE course was in 1981, right? You would look at this and you would have been taught what to do. You probably don't do it anymore, right? But This is something where there's a standard trick, okay? So I'll just tell you the standard trick. You can put this into the kind of constant coefficient linear problem that you can do characteristics on. If you do the substitution, x is the natural logarithm of r, right? So that means r is e to the x. And if you do that, I'll skip the details. Okay, this is something again where if you were old, you would have been taught this. Maybe they still do it. I don't know. This would be the reason to know that technique, really. This transforms into this constant coefficient problem. Which has growing and decaying modes, right? So I'm going to get un of x is e to the some coefficient nx plus b e to the minus nx. This is all for n not equal to 0. If n is equal to 0, I get u0 is just a plus b x. Okay, so this one goes to un of r then. Okay, sorry. Maricela just sent me something funny on the Slack channel. No, it doesn't. No, you have to have other things. Oh, it was from a student. Student says, my back hurts and I'm tired all day. Does that count as being old? No, you guys are young. You guys are younger than my children, so you're still you're still young. Anyway, Maricela says she thought I would enjoy that. I guess she knows me at this stage. We've worked together for a few years now. Okay, now you've distracted me from this stuff. Now, of course, I could have just put n and minus n here without the absolute value, but there's one of the solutions which is okay for the positive n's, absolute value of n's, and the negative ones. So I've written it this way, and so this is going to be when I go back to regular r coordinates. This is r to the n, and this is r to the minus n, right? And so here is where we can see, as r goes to 0, that one is unbounded. So I get to say that b is 0. And if I look at this special case, this one goes to u0 is a plus b log r, right? And as r goes to 0, right, that's one I can cross out, right? So I'm going to have the a coefficients in the series will be left that I'll be able to match the initial conditions to. So I'll have b equals 0, and a will be g n in both of these cases. Okay, so now I'm going to have u of r and theta is a sum gn r to the n e to the I n theta. Okay, so there's something interesting from this before we actually get to Poisson's formula. I'm not sure if I'm going to go through the algebra of Poisson's formula. I'm not sure how useful that is, especially if you've already seen it in a class. But there's some physical insight, the application interest that comes from this formula already. right? So now you can think of the boundary data, the G, right? You've put it into its Fourier components. So large n coefficients are really oscillatory stuff on the boundary, right? Right. So now you have to think as r gets small, right? It's less than 1. Oh, how did we get a is equal to g? N came up. Marisol, I'll save you from typing it in Slack. We have this boundary condition. And so that's just, right? When I've got r is equal to 1, this is 1, and it has to match the boundary conditions. Okay, you got it. So one thing you can see right away looking at this thing is that high frequency components of the boundary condition function G do not penetrate far into the disk. Let's look at what happens at r is equal to 0.9, right? If you've got n is equal to 10, so you've got, you know, something that's got a few wiggles on it, right, around the outside, right? Then when you're at r is equal to 9, you're you're weighted at 0.9 to the 10th power, which means it's actually pretty small, even though you're not very far into the disk. And then, of course, if you're at a half, that's 1/2 to the 10th power. Really, that information is not penetrating inside this disk very much at all. So that's something that you can get. Now, let me just say, a long string of algebra, which is in the notes. So you can do it if you really want to see this. If you haven't seen it in your complex variables class, you can end up with this formula, which is a Green's function representation of the problem. Okay, and so to describe this formula, I have to, I guess I should show you something. Here I'm in this disk. I'm looking for, I've got g of theta, right, for the values of u. I got Laplacian u is 0 in here. And I'm looking at this point, u of r and theta. And so what you can see is u of r and theta depends on g of theta prime at all theta prime, right? This is something that's never 0, right? So this is something that shows you the solution, right, in the middle, anywhere in the middle, depends on everything that you give as boundary conditions. So there's a global dependence on the boundary conditions. This is a typical behavior for elliptic problems. And then I can also say this is a Green's function. It's called Poisson's formula. It's really a Green's function representation of the solution. One of the things which you can show, okay, is that this thing here, which I'll call g of r theta prime, right? Okay, why am I calling it that? Well, this is the map from the data at theta prime to the position inside the disk given by the coordinates r and theta, right? And I'll just say note, G is always positive, right? So that's all of the data on the boundary gives you a contribution to at every point. And also, if I integrate 0 to 2 pi, 1 over 2 pi, G of r in theta prime, and I integrate d theta prime, right? So is this the one I want? Yes, this is the one I want. So this is equal to 1 for all r and theta. And so that's not obvious, by the way, right? There's some work to do to figure that out. And what this tells you is u of r and theta is an average of g theta prime values. Right, so at every point, right, I have is a weighted average of g of theta values. And if you look at the value in the middle, this is an exact average of g of theta prime values. Okay, so so when r is equal to 0, you can see that term's gone, that term's gone, that term's gone. You're just integrating from 0 to 2 pi g of theta prime, right? So it's the average of the boundary values is what you see in the middle. And we'll come back to this either in a lecture or an assignment question. This will prove the maximum principle for the Laplace problem. So that's for any domain. The maximum value of the solution has to appear on the boundary. So you know what the maximum value of the solution is going to be because you've given the boundary data. So if you follow through the things I've mentioned already, you can see that this is going to prove a maximum principle for Laplace problem in the disk, and then you take that and you can extend that to other domains with I think there's one trick you need to pull out to make the general argument, which we'll do, like I say, either later on in another lecture or in an assignment question. Okay, so we got 15 minutes. So the question is, what if you have the Neumann problem? So instead of given Dirichlet data, you're given Neumann data. So that becomes a little bit tricky. In fact, maybe I'll save classification for next lecture because I think it's more than 15 minutes. I'll waste a few minutes here on the Neumann problem. Okay, so let's look at the Neumann problem. First of all, let's get a little bit of intuition, okay? Right? So what is this problem, right? Well, this is the steady state of the 2D heat equation, right? So if I had the heat equation in the disk, it would be, okay, let me confuse anyone who's looking at these later on, right? So I could have du dt is Laplacian u. That's the heat equation in 2 spatial dimensions, right? And I could give, u at x, y, and times 0 would be u0 of x. And then I'll give the same boundary values. G of theta, and these will be independent of time. Okay, we've seen a whole bunch of these cases, right? And what we know is that as time goes to infinity, the heat equation forgets about the initial conditions, right? Whatever they were, they've decayed away. Then du dt, it will only be forced by what's happening in the boundary conditions. Well, they're not changing in time. And so this Laplace problem is the steady state of this heat equation problem, right? So you could imagine, right? You've given the temperature, right, on the outside, and you've just left it long enough so that things have equilibrated inside, right? If you gave G as a constant, right, then the only thing that would be left would be a constant temperature, right? That's a pretty boring Laplace problem, but sometimes boring is interesting, right? If you know what I mean, right? If that's what you got, then you know what will happen, right? But if you've got temperature variations that persist in time, then you'll have some non-constant steady state inside. So let's look at the Neumann problem. Okay, so let's in the disk. Oh, whoop, I'm still blue. So now I want to have a Laplacian of u is equal to 0. And I want to give, the student said grad u dot n hat. So I'm just going to call that the normal derivative, right? I'm going to have an outward normal. So the derivative, okay, now I have to think. If I've got a normal derivative that is positive, this should correspond to heat flux going in. So I'm going to have a g of theta, which now this is going to be the heat flux in to the disk. There's a sign issue here with like which direction you take the normal and what the sign is. I've only really ever got a 50-50 chance with signs, but I think I got it. I think I've got this right. Okay. So let's think of this problem, right? This is also going to come as a steady state of the heat equation. So now let's use a little bit of physical intuition. Is that problem always solvable? I can give you a hint. What if I've got g of theta is 1 all around? Okay, good observation I see coming in, right? This problem only makes sense if g has average value 0, right? Because if I've got a net amount of heat flowing into the disk, okay, the net amount could be negative, which means like I've got a net amount of heat flowing out of the disk, okay, right? But if the net amount of heat flowing into the disk is not 0, then I'll just be heating up the disk over time, right? There'll be a t term, right, in the solution. So there won't be a steady state. So let's be clear, right? I could go back to the heat equation. That problem would be fine, and I would see a linear increase or decrease in the temperature as the limiting behavior. Not steady state, but we could say there's a limiting behavior of this thing. Continues to heat up at a certain rate that depends on the net heat flux. So this problem is only solvable if the integral of g of theta is d theta is 0. Okay, and then the solution is only determined up to a constant. Right? Because you've got this 0 net heat flux in, so you're not growing linearly temperature and time, but what temperature did you start at? Remember one of the assignment questions that you had where the limiting behavior of the heat equation was whatever the average temperature was at time 0. So this constant is like a vestige of the time-dependent problem that you thought you had gotten away from with the steady state problem, right? Right. Whatever the constant, if this was the time-dependent problem, then you would get that constant as from the initial conditions. That would be the only thing that would be left of the initial conditions would be that average temperature. Okay, and I believe there is a formula for this problem too. Okay, but I don't happen to know it off the top of my head. So that would be the Neumann problem. And now you have seen, without seeing, the technical details, at least some physical motivation for how these things go. And there is a condition to be able to have a solution, and the solution is not uniquely defined. This is really an analog of linear algebra ideas for symmetric matrices. If you have a symmetric matrix which has an eigenvalue 0, and you're trying to solve, that's the matrix A, and you're trying to solve A times X is equal to B, B has to be perpendicular to that eigenvector, right? That's this thing. This G has to be perpendicular to the constant. And the solution that you come up with is got an arbitrary coefficient of that eigenfunction. And this is the arbitrary coefficient in the constant. So perpendicular to that solution and arbitrary up to that solution. These are sort of linear algebra ideas. Now, this was an off-the-cuff discussion motivated by a student question. It's okay if you didn't follow all of it, but I thought it was interesting and worth following up on. And there was a good comment from the student about they could anticipate that this would be the condition that would have to be satisfied for there to be a solution. We'll pick up this last topic, this classification of 2D second order PDEs. It's a separate topic, which I'm not going to be able to do in 4 minutes. So I propose we end early. I bet no one will object. I'm going to stop recording, but I'll stick around if there's any questions people have. I'll be happy to answer.